Hello guys, my name is Timothy Mnowa Joseph. In today's lesson, I am going to teach you the conservation of momentum. So you are going to learn about the principle of conservation of momentum. You are also going to learn how to derive the equation, and then I'm going to teach you how to use this equation to solve related problems. So what are you waiting for? Grab a cup of popcorn, sit back, relax as you enjoy the lesson. To start with, we are going to look at the principle of conservation of momentum. The principle of conservation of momentum. This principle states that when two bodies traveling in a straight line collide, the total momentum before collision is equal to the total momentum after collision, provided there is no external force acts on the colliding bodies. So this principle is given according to the third Newton's laws of motion. Yes, which states that to every action, there's always an equal and an opposite reaction. Now I am going to use some diagrams to illustrate this principle of conservation of momentum and also show you how to derive the equation that you need for the calculation. Okay. So let's have our first line here. Let's put another line here. We're going to need these lines, and then we are going to need another line here, and then we need to draw some balls, some snooker balls. So let's put the first ball here, snooker ball, and then we have the other one here. Let's put it here, and then we are going to put two balls here, the same balls. Okay, and then we are going to have another balls here. Never mind if their size is different, but I'm just going to adjust them to have the same size. Let's see if we're going to achieve that. And then this sticks together this way. That's collision. And then we have this. Okay. So now I need arrows. I'm going to explain this to you. So this is direction is here, and then we have this. This is during collision, and then after collision they gain certain momentum, certain final velocity. Okay, so we are going to call this ball A. I'm going to explain. We have two snooker balls, so this is A, B, this is also A, and this is B, A, B. They are the same balls. Okay. These two balls are at rest now. They are at rest, and then which means their initial velocity, I'm going to select the U. The initial velocity of this is going to be given as UA, and so UA, we're going to use sense of this ball here. It also has a certain mass, and then the initial velocity of this is going to be UB. Okay, these are two different balls at rest. So this is before impact or before collision. So I'm going to write it at this corner, before impacts. So impacts and collision means mean the same thing. And this is during impacts here. during impact, or if you want to say collision, during impact, and then this is after impact. So after impact. So before impact, this ball has a certain, has an initial velocity of 0 because it is stationary. It is stationary. This is also stationary. So the initial velocity here of these two balls are just zeros. And then here, this is during impact, and then they gain final velocity here, which sets this in motion in this direction and also this ball in motion. So we are going to call this final velocity of A and then final velocity of ball B. Write it here. Now, you know that momentum, which is represented by a small letter p, is given as m times v, that is the mass of the object times its velocity. So to find the equation of the conservation momentum, since the principle states that when two bodies traveling in a straight line collide, the total momentum before collision is equal to the total momentum after collision, provided there's no any external force acts on the colliding bodies. So I'm going to write it here, which means that total momentum before collision, that is the total initial momentum. So let me just write it here for you to understand. So the total initial momentum, this is before collision, initial momentum is equal to the total final momentum of these two balls or of any object given to you. So this is what the principle of conservation of momentum states. All right, so now since the total initial momentum is equal to the total final momentum of these two colliding bodies here, so we are going to find the momentum of this ball A, which is going to be MA times UA plus MB times UB is equal to the total final momentum, what we have here. So which is going to be MA times VA, final velocity, plus the momentum of this guy, MB times its final velocity. So this is what the principle of conservation of moments states. You can see how we generate this equation. So this equation will be needed for calculation, but in case if the colliding objects stick together as a result of the collision, they have the same final momentum. So supposing this after collision, they stick together like this and then travel with the same velocity. They travel with the same velocity. So we are going to have this equation. So this remains. So we're going to have something like this: MA UA plus MB UB is equal to, since they are traveling the same with the same velocity, so we are going to just take one velocity here, the final velocity. Here we have MA plus MB. So take note of this equation too. We are going to need this equation as well. Let's take a look at this again. So what do I need to explain again? So this M stands for the mass of the object A, the ball A, and then its initial velocity is given as this. And then MB stands for mass of this object as well. And then UB stands for the initial velocity of this object. And then here we have MA, which stands for uh, the mass of this object, and then VB is also given as the velocity, final velocity of this object, and as well as VA, which also stands for final velocity of this ball A. In some textbooks, they may decide to use something like this: M1 U one for you, it also means the same thing. Something like this is something like this, means something like this, or they may, yes, or it could be written as this again. I'm just trying to explain to you so that whichever one you see or you have in your textbook, you will not be confused. M1, V1 plus M2, V2, something like this. But I am using letters in this lesson. Okay, you can take a look at it again. Now we are going to solve some examples to show you how to apply this formula. Okay, so I'm going to get rid of this right away now. Okay, so let me clear the screen and then we proceed. This is our first example which we are going to consider. A rail wagon of mass 3,000 kilograms moving at a velocity of 1.2 meters per second collides with a stationary wagon of mass 2,000 kilograms. After the collision, the two wagons couple together. Calculate their speed immediately after the collision. Couples together here means they stick together and travel with the same velocity. Okay, so I'm going to use diagram to illustrate this for a better understanding of the lesson. So let me quickly interpret the question. So I want to interpret the question. Okay, so let's take this as our first wagon. So I want to be quick because so this is the wagon here. So a rail wagon of mass 3,000 kilograms moving in with a velocity of this, and then this is the second wagon that it collides with. So let's put that here. The second wagon is going to be here. So let's say this is the second wagon. I want to, the second wagon here. So this is the collision. This is showing collision. Okay, so let's put the wheel right away quick. So this is going to have its own wheel and the other one is going to have its own wheel. Don't mind me, I just like drawing, so we need to give a proper interpretation. So this is the wheel of this wagon and then this is the wheel of this wagon as well. So, okay, so let's shape this wheel and make it beautiful. Let's bring it here and then, okay. Right, so this is the wagon and then let's give this one its own wheel too. So this is having its own wheel and then this is also the second wheel. Okay. Okay, I think it's okay this way. So shoot the wheel, shoot wheel here. All right. So this is a rail wagon of mass 3,000 kg. So let's put the data inside this. The data we have, the data that we have here. So let's quickly put the data now, and then we solve the problem once and for all. So we have this. The mass of this is 3,000 kg, and then the mass of this uh, is how much? 2,000 kg. Okay, and then This is traveling with a certain velocity. So let's just bring out what we have in this question. So we have, we should have our, so let's call this one A and let's call this one B, right? So we have mass MA, which is 3,000 kilogram, right? And then we have the initial velocity of this is 1.2 meter per second. So we are going to write it as this 1.2 meter per second. And then we have mass MB, so which is going to be this equal to 2,000 kilogram. Its initial velocity, which is going to be, uh, sorry, is going to be UB, right? So we should have UB here, which is going to be 0. Why is it 0? Because it is stationary. It is stationary before the collision. So this rail wagon collides with this one, a stationary wagon here. So the initial velocity is 0 meter per second. So we can write it as this. And then they stick together, that is coupled together. They couple together, which means they stick together, and then they travel with the same amount of velocity, final velocity. So we are simply looking for this final velocity here. That is what we don't have. So how do we do this? So we are just going to apply uh, the law or the principles that you have learned. Now, do not forget that momentum is given as this. Yes, I've talked about this. Now, we want to apply the equation. So let me quickly divide this screen now so that we can do the solution. Okay, so we are going to apply this equation, that is the total initial momentum is equal to the total final momentum, and then we have something like this. The momentum of this, right, plus the initial momentum of this B, this one, times this, it is equal to the final momentum now. So which we are going to have MA times VA plus MB times VB. So we are going to have this. Yes, I want to explain something. But remember that I told you that when they stick together and they have common moment, common velocity, which means they are traveling with the same velocity as this question has stated here, coupled together, which means stick together. So what we are going to do now, they travel the same momentum. So we are going to have something like this: MAUA plus MB times UB, it is equal to, we just pick one of these velocities and say MA plus MB. And then we substitute this information into this. You can see that it's very simple, right? So we're using this equation. So let's see. So our MA is 3,000. So we have 3,000 kilogram times UA initial velocity, which is given us 1.2. That is what we have, 1.2 meter per second. Then plus this. So you can bracket this, you can put in brackets, plus MB. The mass of MB is given as 2,000 gram, sorry, kilogram, 2,000 kilogram. Let's put this in bracket, times its initial velocity is 0. So we are free to write 0 here. Then equal to V bracket MA, which is 3,000 plus 2,000, right? And then we put everything in brackets. So 3,000 times 1.2, let me quickly punch calculator and get the answer. So we have 3,600 here plus 2,000 times 0. We don't need to punch calculator for this. It's just 0. And then we are going to have V times these guys here, 3,000 plus 2,000. We are having 5 5,000 V. So let's just quickly write 5,000 V's, 5,000 V here. And then what again? So this becomes so simple. So we have 3,600 equal to 5,000 V. Therefore, we say our V dividing both sides by 5,000. We are going to write this guy like this. Yes, yes. So this 20 take away this. Okay, using calculator response. So we have 0.72. So we can say our velocity, that is the speed, their speed immediately after the collision is 0.72 meter per 0.72 meter per second. So we can body write that their speed is 0.72 meter per second. Immediately they stick together. Okay, you can see that it is very simple. See how we apply the equation. Yes. So let's take another example and solve. Okay. All right. So let's consider the second example, but first we need to clear the screen so that we can have space for our calculation. Okay, so let's look at this question. It says that a rail wagon of mass 5,000 kilograms moving at a velocity of 1.6 meter per second collides with a stationary wagon of mass 3,000 kilograms, and after the collision, the 3,000 kilogram wagon moves away at a velocity of 1.5 meter per second. Calculate the speed and direction of the 5,000 kilogram wagon after the collision. So again, we are going to quickly use diagram to illustrate this. Just going to quickly put the diagram here again for our illustration. So let's see, this is station wagon here. The rail wagon right there. So we're having a rail wagon here, and then we have the second one. Sorry, I need to change this. Okay, so we have it here like this, and then we have the second one, which is stationary. Uh, we have it here. So we have it here, and then let's quickly draw the wheels now. The wheels now. So let's do this on this one wheel. Okay. Okay. Let's just width. Okay. And then let's also give the second one its own wheel too as well. Okay. So these are the wheels. Okay. So let's adjust this too as well. All right, let's go back, and a rail wagon of mass 5,000 kilograms. So which means this is 5,000 kilogram, this one 5,000 kilogram, and then the second one is 3,000 kilograms. So we can write that here, 3,000 kilogram. Okay, yes, right. They are traveling with certain, this one is traveling with certain amount of initial velocity, which is given as 1.6 meter per second. And this one, it is stationary. So its initial velocity is going to be 0. So I'm going to put it here. Now, so the initial velocity of this is 0. So let's put it down. So our initial velocity is 1.6 meter per second, and this one is having an initial velocity of 0, but final velocity is given as 1.5 meter per second. Okay, right. So we can also write out the full data. So let me just help you. So the final velocity here, we don't know. It's not given. So calculate the speed and direction of the 5,000 kilogram after the collision. So this one. Okay. So let's call this one A again, and we call this wagon B. Okay. So we just write out what we have. So our mass A is 5,000 kg. Then initial velocity is given as 1.6 meter per second. And then mass B here, this must be, what do we have? We have MB, which is 3,000 kg. And then its initial velocity, which is UB, is given as 0. 0, okay. And then, but we have its final velocity, yes. Final velocity, which is VB, it is given as 1.5 meter per second. Here, the final velocity is not given, so we are going to look for it. So take a look at this question. So we are going to calculate the speed and direction of the 5,000 kilogram wagon after the collision. So after the collision, they move towards the direction that is forward. So let's apply the principle of conservation of momentum, the equation. So we have our equation as this. Let me quickly divide the screen again for easy solution or working. So let's divide. Okay. So we have this equation. The initial momentum of this body here. So we have this times this, then plus MB UB is equal to MA times VA, yes, plus MB times VB, that is final velocity. So when you look at this question, there is no coupling. So this body did not couple together. That is, the two rail wagons did not couple together. So no, there is no sticking together. So they tend to move apart. So we are not going to apply the other equation, but we are applying this equation to solve this problem. I'm sure you understand now. So let's just put in our data into this. We substitute now, and then we get the answer. So our MA, which is mass of this, we have 5,000 times UA. What is UA? 1.6 meter per second. So 1.6. So that is what we have. Then we can bracket this as usual. So plus mass of B, which is 3,000. That is mass of the second wagon. 3,000 times its initial velocity, which is given as 0. So we have something like this. Why is it so tiny? So something like this. So let's bracket this, and then we have this also as well, equal to mass of A. So we can write it there, there's no problem. So mass of A, which is going to be 5,000 again, times VA, which we don't know. So we don't know this VA. So let's write it here. So VA plus mass, I'm not writing the mass again. So mass of B, 3000 times its final velocity, which is given as 1.5 meter per second, right? So we can separate them by using our brackets. Yes. Okay. All right. So now let's find the result. So 5,000 times 1.6, we should have, let's quickly confirm this by using calculator. Okay. So we have 8,000 here. Okay. And then plus 3,000 times 0, definitely 0. So equal to 5,000 times VA. So we have 5,000 VA plus 3,000 times 1.5. 3,000 times 1.5 from calculator. Let's punch calculator and see what we have. So we have 4,500. 4,500, right? Okay, so if we rearrange this equation, rearranging this equation, we are going to have 8,000 plus 0 is 8,000. That is collecting like 10. So this one comes here. So yes, we should have, sorry, I just speak Russian. I'm sorry, no. Нет means no in Russian. So, okay, so minus this guy equal to 5,000 VA. So taking away this from this, we should have 3,500. Yes, we don't need calculator for this. Equal to 5,000 VA. Yes. So at this junction, we should know what to do. So definitely our VA is going to be 3,500 divided by 5,000. Yes. And what do we have? Yes, what do we have? So we have 0.7 meter per second. Yes. So this is the velocity of this rail wagon. Yes. After the collision, this is the velocity here or the speed. I'm going to use velocity because it has direction. So calculate the speed and direction of the 5,000 kilogram wagon after the collision. Of course, the direction is forward. So it is going in the same direction which the wagon B. So it's going this way. The direction is this way. So they have the same direction. So the same direction. If you want me to write it, the same direction. Yes. Okay. Because it's going forward. How do we know? Because again, the velocity is positive. Yes. Our velocity is positive. So the same direction is positive. Okay, guys, thank you for taking your time to watch this video. This is where I'm going to stop. Please do like this video, share it, and comment about it. Feel free to ask me any questions regarding this lesson if you need any clarifications, and I'm going to answer you. Thank you once again. Goodbye.